So now I would like to talk about the ANAC, which is for averaged so maybe as a background in general relativity, you have the Einstein equation. My stress tensor is theta. I'm using a t for some other things. And of course, if you have any metric, any Lorentzian metric, you can, of course, compute its Einstein tensor and then define the stress energy tensor to be just that, and you have a solution. It's, of course, not a very meaningful solution. So the real thing you should be doing is to write down the stress energy tensor and then solve for the metric, or rather you write down the stress energy tensor and you solve for the matter fields and the metric. But oftentimes in general relativity, if you want to understand things about the space-time metric, or a metric solving this equation, you're not really, in every case, need the complete details of this object, but you are okay with certain general conditions. And one such conditions are energy conditions. So there's the null energy condition, dominant energy condition, and various other things, strong energy condition. So I'm not reviewing them here, but the null energy condition is just that it's supposed to be not negative for any null vector k mu. So any. And why is that an interesting condition? Why is that? Why do you? So you know that the Einstein tensor is Ricci minus a half this piece. So if you contract this twice with a null vector, this piece does not make a contribution. So G mu nu, therefore, which is related to this by the Einstein equation. So this is the same as R mu nu. And by this condition, you thereby find that the Ricci tensor dotted twice into the null vector has a sign. And now why is that interesting? There is an equation called the Raychaudhuri equation. So it's just a name for the null-null component of the Einstein equation, nothing more. So if there are some components left in the Einstein equation, you can just take them and give them your name if you do something with them. So it's just a component of the Einstein equation. But the Raychaudhuri equation, if you take an affine parameter, lambda, so it says that the expansion is minus, so this is another theta, is a little theta, a small theta. So this is the expansion of a null congruence tangent to k mu, and this is the shear on the shear squared. There are some coefficients that depend on the dimension. So there's just some numbers in front, which all and on your conventions for defining the shear and the expansion. I'm not careful about this, and this is your Ricci term, and lambda. This lambda is an affine parameter along the congruence. So the picture is something like this. So you have some congruence that you set up tangent to k mu suitably. So these are all supposed to be parallel here initially. Maybe I should also draw them like that. Set them up parallel. That means congruence. And then they pass through some curved geometry, and they will do various things. So you can compute the area of such a cross-section, and then later, and how this area changes is the expansion, or infinitesimal change. Everything is infinitesimal, and this is supposed to be an infinitesimally small area element. So this is the lambda this is k mu, and lambda is along congruences, and the area, the rate of change of the area, roughly, that's the expansion. So, as you know, in general relativity, a geodesic corresponds to a freely falling observer or freely falling object. These are, of course, null geodesics. And so they don't feel any acceleration. And so if the expansion is positive, then they diverge from each other. So, and if the expansion is negative, they converge. Yeah? So this is related to focusing or defocusing effects. So this equation is nice because all terms here have one sign if the energy condition is fulfilled. So negative. So this is for starters not a sign of the expansion, but of the derivative of the expansion. So this means that the derivative of the expansion has a sign. So if something, let's say, contracts, it will contract more and more. That's what this says. Yeah? So it doesn't say something immediately about the sign, but about the derivative of this. So it is used in the singularity theorems for this reason. You know, because you can learn about focusing effects. So this is basically one reason why it's interesting to it's relevant to just know about some certain sign of the stress energy tensor. And so my colleague Gern in Leipzig, he once said that in these theorems you shouldn't think of the Einstein equation, but you should think of it as the Einstein inequality, because what you're using is just a sign of some things and not really an equation. I think that's a really right way to think about it. So it's the Einstein inequality. Of course, in a real model, you have a microscopic. Usually, you have a microscopic model for the matter field. So I mentioned the Klein-Gordon field, phi, and then the stress tensor would be something like minus 1/2 g mu. Yes. And then yes. This would be the formula for the Klein-Gordon field, and it's easy to see that in this case you have, if you drop that into twice, this is a matrix, so if you contract it into a null vector, it doesn't contribute anything. So you're only going to get a contribution from this term, which you can write as a perfect square. So in this theory, obviously, since a perfect square can't be negative, you have the null energy condition. So you can do the same exercise for the Maxwell field, non-abelian engaged field.
If you have an expanding universe, what's the meaning? That it will expand less and less?
More and more.
More and more.
Yeah. So what you usually then think of it is in the past, so it will contract more and more. So it gives you, so there are different statements, then there's the sort of, you can use it to derive a cosmological Big Bang type singularity or geodesic incompleteness. This is by itself not the only ingredient in the proof. This is just a local ingredient. Of course, you can, even in flat space, you can have completely harmless things, something like a caustic, where you have some geodesics. Now here they are initially expanding, but so they can do something like this. They can enter the light cones of a caustic if you have a beer glass or something, and you can see these bright spots, and that would be here. And so in here also, this expansion would become infinite. But there is nothing singular about this point, really. It's just it's just a caustic. So this is usually combined then with some global information where you apply this to a globally defined null sheet, like the past of the boundary of the past of future infinity, where you know that such kind of things for global reasons cannot occur. And so if they do occur, somehow it must therefore be related to some pathological. So this cannot occur if you have a nice space-time. And so if they do occur, it must be related to some actual singularity. So it's the combination of these two arguments. And also in the cosmological setting, you have some global part of the argument. So the local part is, I think, was already understood long before Roger Penrose and others. But it's this global part of the argument that was really this new ingredient by Hawking and Penrose. Okay, so now in curve T, the neck does not hold simply. And why? So it's basically because of quantum mechanical interference. And I have this example in my lecture notes, which I took from a paper by. Yes?
Curiosity. In Euclidean space-time, the neck
yeah, then it's some condition on the Ricci positivity of the Ricci tensor. So that it means just that the Ricci, there are no null vectors, of course. It means that the Ricci is a positive definite quadratic form. So it also has consequences. Riemann geometers have many theorems, like what happens if the Ricci tensor, if you have certain conditions on the eigenvalues of the Ricci tensor, and what that means for the geometry. Many results like that.
So it's equivalent one. In general, all the energy conditions can be reformulated in Euclidean.
No, it's really a Lorentzian thing, though I'm just meant to say that you can also, and people do impose such some various conditions on the Ricci tensor, like all eigenvalues positive, all eigenvalues negative, or some eigenvalues always dominated by others. There are tons of theorems, but their consequences are different things usually. Yeah. So for instance, if the eigenvalues are all negative, then asymptotically the space is like a ADS space and things like this. Okay. Now I wanted to tell you why the neck doesn't hold. You can actually prove this, but I liked better this example. And as I said, it's due to Larry Ford, I think. So you can look at the Klein-Gordon field, where this stress tensor, in fact in Minkowski space, and so the stress tensor would be just the quantum operator, and in Minkowski space it really just is the normal ordered operator. So the phi, so you would write your field phi as this would be the field, and then you can formally write down this expression, and you normal order it as you learn in your Q of T course to get a well-defined operator. So like this, and now you can look, for instance, you can define a two-particle state, a superposition of the vacuum and a two-particle state. So in general, something like this, D3. Put some wave function here. I'm going to explain. So this is a bosonic wave function. This is a two-particle momentum eigenstate. So this would be, just make sure I got my normalizations right. So this would be a mega. And now you can, I'm not going to look at the null energy condition. I'm going to look at even just the energy density. So you can compute just the 0, 0 component of this. You can also compute the null component, but it's slightly more complicated. The 0, 0 component also is positive. You can also classically write it as a sum of squares, and because you have a 0, 0 squared here, and then if you work out the signs, this is minus a half times phi 0 phi 0 squared, and this gives a plus. So this can also be written as a square, and you can compute this based on some concrete answers for this, and I'm taking to give you the intuition where this is really coming from. So they, Ford et al. Make this following ansatz. This is not the only possibility, but it is possible. So pi of p, and then p1, p2 times a certain power is half, and this chi, the chi is a step function. in such a way that so chi of p is 0 if p is less than some p naught, and chi of p is 0 if, let's say, it's bigger than 2 p naught. And then also you also say C0, C2 is 0 if P1 greater than some cutoff. So you have make this ansatz. So what does it correspond to physically? So P, this means that the wave function, the two-particle wave function, that's what it is peaked where, because of this condition, is peaked roughly when the momenta are opposite. Yeah, so the sum of the momenta should be 0. So this means basically P1 is roughly minus P2. So you have two colliding waves, basically, with opposite momentum. And so if you write one wave like this, then the other wave will be sort of slightly tilted. And the momentum goes this way and that way. And in this case, because it's a superposition, you're going to get an interference effect from the two waves. And if you do the calculation, this interference effect, let me write a space-time picture. So something like this. This is t and this is x. So let's do something like something like this, or the wave, and the other wave is going to be have the opposite momentum, be something like this. And so you can kind of see that when the waves can constructively or destructively interfere, and you're going to get a pattern if you then plot this thing, which has an alternating positive and negative parts. So you see just a simple calculation. And furthermore, these patterns will always alternate in any time-like direction. So you can do this calculation. I think it's nice if you can just do a Mathematica script, a little one, and just plot it. I think that's the most efficient way of doing it. You have these three parameters, nu, chi naught, and the cutoff, which you can still tune. Yeah, of course, you should also demand that the state is normalized. So this gives obviously some condition, visual quantum mechanics. And so you see that it's you in particular have pieces where this is negative, but because it's an interference, it must always alternate with something where it's positive. Yeah, that's the idea in quantum mechanics. You get these interference patterns, but they kind of alternate. And so if you may think that therefore while this can be, if you're just in a negative dip, it can be negative. But if you integrate over time, sooner or later it will be followed by a positive dip, and so on. And so you may think that if you integrate over time, the positive dips will eventually win. That's the idea behind this average conditions. And in fact, you can I like this one quite because you can just work out everything just using really basic intuition, really basic formulas. It's just a bit tedious, and you can also look at the paper. It's of course was done before. So the conclusion from this example is that in the expected energy density T of X, which is in this case the 0, 0 component, as T is varied, fixed X, and positive and negative values of rho alternate. And even though the negative ones can become arbitrarily negative, you can observe in this example that then they must be followed by an even more positive piece. Yeah. So if you really want to set this up in a measurement, you have to be quite careful and really find those negative pieces, these kind of negative values with high resolution. So that's so the idea, therefore, is that maybe if you took some integral of this, let's say T and X, is the energy density. So if you took some integral of this, and maybe you would have here some probability distribution, sampling function, window function. So the idea is that this may perhaps always be positive. Yeah. So you cannot somehow beat this. So this is still not quite true because you can take the window function so that it sits exactly in the negative ditch. But then you will be in general be punished by having a large derivative of this. So this is not actually true. So the real inequality is that if you put a bound on the derivative of this, so you cannot localize it in just a valley, then this cannot become too negative. But another way is to just, in a way, keep this just constant and just average. So this cannot be done with this energy density, but it can be done arguably with the null components. So something like if you take kk and d lambda. So k is again my null vector. So for example, it could be 1, 1 and 0, 0, if you like. And lambda is the affine parameter. The curve tangent. So the NX is the statement that this is supposed to be positive. And the NX, so it avoids this averaging function. But the idea is the same, that though this integrand can have both signs, the positive part will dominate over time. So A is for average because this is an average. It's not really an average, it's just an integral. Now, it's not obvious that this is true, though. So in flat space-time, it is true. And also if k mu is tangent to a Killing horizon, so something like the horizon of Schwarzschild space-time, that's a typical example of a Killing horizon. Yeah, this is arguably in total generality, and this also in total generality. It is okay, but in general, it's not okay. So if you take an arbitrary, even for Klein-Gordon, if you, in a curved space-time, you take an arbitrary null congruence. So certainly you can find null congruences where this is not positive. So an example is, of course, this T mu nu is very difficult to calculate. But if you, for example, what we calculated in recent years a lot, so we calculated something like the stress tensor we calculated the stress tensor in Kerr spacetime, in Kerr spacetime, not curved spacetime. So a Kerr spacetime has something called an inner horizon. And you can calculate the stress tensor or the null component at the inner horizon, and it can be infinitely negative even if you integrate it all the way. So it doesn't always hold. So the idea what people believe, but that is quite far from a proof, is that a back reaction enforces the NX. So in other words, if you do just a fixed a quantum field theory on a fixed curved space-time, it may not be true, but if somehow the space-time is a semi-classical solution to the Einstein equation, meaning that G mu nu in some sense is 8 pi times the expectation value of the stress tensor in the state, then it's supposed to be true. So there is no proof of this. There's a paper from Bob Wald and Ina Flanagan from the 80s where they argue, or they give evidence for this, but it is kind of generally believed. Okay, but in Minkowski space, it's okay. So you could do this. It's instructive, actually, to do it in this example, where you can just, this is not a proof of this, because this is supposed to be a general statement for any quantum state or any regular quantum state, and not just a superposition of a 0 and a 2-particle state. But for free field, it's kind of just the essential idea where this is coming from. Now, I want to spend a bit of time on this now, because it's related to something called a half-sided modular inclusions that originated in algebraic quantum field theory maybe something like 30 years ago, due to going back to work of Borchers and Wiesborg and people that were active before I even knew what algebraic quantum field theory was. So I'll explain what the half-sided modular inclusion is. It wasn't originally invented, I think, having this in mind, or I don't honestly know, but I'll explain what it is, and the connection is still a bit heuristic, I would say. The concept of half-sided modular occlusion is totally 100% mathematically precise, but the connection to the ANAC, I think, is a bit heuristic, but it's without doubt correct, in my opinion. So let me explain what a half-sided modular occlusion is, and maybe how it's related to the ANAC, and then maybe move on to something perhaps even more interesting called the QNAC. So since we know about modular operators, let me first state abstractly what is a half-sided modular occlusion is. So what we have is two von Neumann algebras, N and M. So not one, but two. And we have a vector in the Hilbert space on which the von Neumann algebras act, which is cyclic and separating for both N and M. So that's not it. So then we have, as you know, we have the modular operator, and the idea is if you so this is the modular operator for M. So let me emphasize that it's for M by putting an M here. So it of course can act also on N. The idea is that this remains in N for t greater than 0. So this is these three conditions. Okay, so the picture that you're invited to consider is where M. Yeah.
So you mean M?
In N, yes.
In the big algebra. It's always in M.
In M is always there, but in N it is. Maybe I did. My letter was a bit strange. Okay, so M is the so this the characteristic example is the algebra of a right wedge in Minkowski space. And then I can consider a cut here. So let's first consider 1 plus 1d. Let this be some distance t. So and so then I get another wedge. Let's call this WT, and W is the whole thing. So right again, M is a W, and N is a shifted wedge. And as my other colleagues explained to you, in this example, we know what is the modular flow of M. It's the boosts. And so obviously, the boosts will move this wedge inside itself for positive times. Of course, for negative times not, but for positive times it will move it inside this wedge. So this is therefore an example of this half-sided modular occlusion. Now I'm going to draw picture with more dimensions, hopefully. Okay, so this is supposed to be okay. So now this is supposed to be a wedge in more dimensions. So there is now an edge of the wedge which has a codimension of 2, and so this is the edge of the wedge. And then I'm going to call this direction x plus, and I'm going to call this direction x minus. And now my algebra n is still a of the wedge, but I can take advantage of the fact that I'm in higher dimensions. So in this case, in 3 dimensions. And now comes the difficult part of the drawing, I suppose. You can so here this apex characterizing this shifted wedge is just a point, but really in higher dimensions you have more directions going this way. So you can think of this cut or this cross section as being characterized by the fact that x plus is some non-trivial function, a positive function of the edge coordinates. Yeah, I think it's clear. I think in other papers there are better drawings. So then again you have this other wedge, this wedge T, which is again inside. So this also for any positive function or smooth or whatever, this is again a half-sided modular inclusion. Okay. This is the setup, and so what's the basic structure theorem about half-sided modular inclusions? So the point is you have, because of the second condition, you have 2 modular operators. Namely, you have this one, and you have, for the same vector, you have the modular operator for the other algebra. So you can, for instance, consider this kind of a combination. It's a unitary operator. And it turns out that this unitary operator can be written in a certain way. So you can be written as the exponential of I times 2 pi t minus 1 times some operator I'm going to call E sub t. So in the math papers, this is usually called P. So I'm going to call it ET. And so the point, the structure theorem is that ET has a positive spectrum. And then it satisfies these kind of relations with this modular operator. So this one, of course, you know what it is. This one is a boost. But this one, if the edge is curved, you do not know what it is. So though you can relate it to something, and this ET, you can consider this for different t's and work out the commutators, or at least formally for different t's, and you realize that the ET and the omega together, or sort of the operators e to the I et and the operator it omega m. They generate a representation of the so-called or part of the so-called BMS group. I'm not going to explain what the BMS group is, but I'm going to explain in this example what you get. So in this example, in this 2D example, E t is just, so here t is just a number. So t is t times the p, I guess it's an upscale, p plus component of the energy momentum operator. So P is the energy momentum operator, which in 2 dimensions is minus the Hamiltonian and the momentum. So and P plus is the Hamiltonian plus is the plus component. So X plus is this null direction. X minus is this null direction. And so this in this case, this is this is a null translation, and this is a boost here. I already have t, so in a way I already have a parameter. Yeah, but I could put a parameter. Yeah, so for a fixed t, yeah, you're right. So if I consider t as fixed, then I have 2 parameters a and t, little t, and the group that's generated by just this for fixed t is just the affine group in 1 dimension. So the ax plus b group, yeah, affine transformations. And so that's kind of expressed by this relationship. But sort of heuristically, the point is that you can think of ET because of these relations with the BMS group. You're invited to think of this as the following. It's the stress energy tensor, the plus component of x plus, x minus 0, and za, and then d to z and t. X plus. So it's a null component of the stress tensor integrated over this, along this sheet, going backwards and forwards. So the motivation why you say it is because of the commutation relations that these things have, and you say that formally they have the same commutation relations as this object would have, and therefore you say they're the same. Yeah? But this is not the first part of the proof. That's rigorous, but this, and I also put it in quotation mark, is not rigorous because, for example, the notion of half-sided modular inclusion nowhere even mentions a stress energy tensor. So you could think of a quantum field theory which just doesn't have one. There are such theories, and so it's under additional assumption somehow that there is a stress tensor and so forth. And so so the average null energy condition basically follows. So because you know that the expectation value of this is positive, that's nothing but this condition. And then you not only that, but you know it's positive for every positive function t. So if you imagine you put t equal to a delta function, which is positive. Then you pick out the value of theta plus plus integrated over x plus at a fixed value of z. Yeah, so this would then be the integral over one null generator. So the ANAC follows by taking t of za to be a delta function of some reference. Okay, so this is a proof of the ANAC. As I said again, there is no, this is a rigorous theorem, but the connection with the stress energy tensor is not totally watertight. And I think that last part would still benefit from some rigorous work, I think. But it is a moral proof of the ANAC. Okay. Now you can also write down a formula for the modular operator with a smaller wedge. So again, you can kind of say maybe this. You could maybe write it in terms of a formal density matrix. So again, if you take the trace over the complement of this wedge, if I had color, maybe I could not quite look quite so messy. So you can look at the complement of the wedge, which would be kind of this thing. And you can take the complement, look at the reduced density matrix of this shifted wedge, which is what you get when you trace out over the complement. And then this is supposed to be equal to, I call it KT. And KT is a similar expression. So here you take x plus minus So in a sense, you have also a formula for the modular operator in terms of the stress tensor in this case. Okay, so this is not quite honest business, because actually this, you should really draw this in a space-time, in a Penrose diagram to see. So this would also have a contribution from future null infinity and from time like future infinity, as with this one. And this should, strictly speaking, be taken into account. Okay. So this is what I wanted to say about the ANAC. I think it's very pretty, but it is, I think from a rigor mathematical viewpoint, it would be satisfactory to make this connection between the stress tensor and the generator that you get from the half-sided modular inclusions more precise. You would have to make certain assumptions, I'm sure. But that in my mind has not really been done. Okay, so there are the questions about the ENIAC.
Should we take a break?
Yeah, maybe. And then they can ask me privately.
Okay, so we resume in about 5 minutes.
Yeah, so now I'd like to continue a bit on this theme and point out to you the connection with something called the generalized second law. I think it was mentioned yesterday by Michele Girafici, and I'll maybe try to expand a bit on it. So the generalized second law, GSL. So what's the second law? The second law is that the entropy must increase or cannot decrease. And now, what's the entropy in general? It's not totally easy to define if you have non-equilibrium, but you can imagine that you can kind of define the entropy of a quantum field on some space or space-time, and you can you supposedly can define the entropy of the black hole itself, which is 1/4 of the area. And the generalized second law, as was already mentioned, is the idea that one or the other can decrease or increase, but the sum of the two cannot decrease. That's in the sense that generalized second laws generalized because you have to take into account the black hole itself. You cannot just work just with the matter fields on the black hole spacetime. So it's originally, I think, due to Bekenstein. So somewhat strangely, still to me, there is an actual argument for it, which I'm going to sketch. Though it's a bit strange. I think it's strange because, and I have no explanation for it, in that the entropy of the quantum fields involved in this second law, in this formulation, is the entanglement entropy. And the entanglement entropy is not really the thermodynamic entropy. It's some sort of measure of correlations of a system with its environment across a boundary, but it's not the thermodynamic entropy of the system. It's really something physically different. And so even though this is called the second law, the generalized second law, there's to me something strange about it. But anyway, so the setting is Schwarzschild space-time. So which has a future and a past horizon and infinities. And then we have a state called the Hartle-Hawking state, which is a state on the entire Space-time is a pure state on the sort of double copy or whatever you want to call it, the Kruskal extension. So it's a pure state. And it's I've described its construction or outlined its construction. So it's most easily constructed by, let's see, at least for free scalar field, by taking the analytic continuation of the outside, where the compactification, where time becomes the Euclidean time is a circle of whose length is the Hawking, the inverse Hawking temperature. So you analytically continue backward, you get this mixed state, and so I'm still going to call this a wedge. I'm calling it wedge. Yeah, I'm calling it a wedge. I don't know, it's not, of course, a wedge. So if you take the trace over the So all these formulas with traces are formal. I just write them for intuition. So the statement is that this is minus the Hawking temperature times the boost, and K is the integral over H plus theta mu K mu similar contributions from there. The beta H is 2 pi divided by the surface gravity of the horizon. So that's the idea here. I've already explained that. And now we have the logarithm of the modular operator, or the Hartley-Hawking state in the wedge. And the modular operator will be something similar. So it will basically be the logarithm of the, how did we call the reduced density matrix, rho something like this. Is all in quotation marks, and the logarithm of this modular operator is that is beta H minus n. This is the same thing, but these are formal expressions. This modular operator is better defined, and it's more or less the same thing, except that you integrate from all the way here, whereas for the reduced density matrix, it's sort of only the half of this integral. Yeah? And it's trying to halve this to really decouple the left and the right which is a technical problem. So now I'm going to look again at this sort of situation with that I described with the half-sided modular inclusion. I'm going to maybe consider it a Cauchy slice and one like this, which intersect the future horizon in different cuts. So if I look at, then I get a wedge, let's say, as the causal completion of this region. This is again WT. And so the WT defines the setup of half-sided modular inclusion. And then I get an operator, thereby I get KT, as I described in just before, which is so I'm using here K, big K, for the generators of time translations. And I'm using also little k as an which is tangent to an affinely parametrized null geodesic. Null. Okay, so both k, big K and little k are both tangent, both null, but one is affinely parametrized. So it's affine. Do you know what's affinely parametrized? It's a general relativity notion, yeah. And the other one is the killing field, which is not affinely parametrized, because it's actually accelerated. Yeah? So the big K satisfies this equation. This big K. Too many K's here. So and then there's also kappa, Stiffest gravity. Another K. Yeah? The little K satisfies a different parameterization. Yeah. It's useful to have both somehow. Okay, so this is K, and then there's plus terms from plus, and the reduced density matrix for this shifted wedge, now for the Hartle-Hawking state, is e to the minus beta. No, I think it's now just 2 pi. To be careful here. This is 2 pi. So before I had beta. Oh yeah, sorry, another K. So with 1 K, this K is the generator of time translations. Maybe I should call it H. Anyway, it's conventional to call it K. Right. And so the difference between 2 pi here is because if I take this K has kappa plus relative to this affinely parameterized K. So that's why there is that's why this is not beta but 2 pi. Okay. This is the reduced density matrix from the half-sided modular inclusion theory. Okay. Now I can also compute the difference between the modular operator and the Hartle-Hawking state and the Hartle-Hawking state of the shifted wedge. And that's, just have to be careful now about all my signs. And that's going to be integral of t eta mu nu as nu, because this t here factors out. So I'm choosing affine parameter such that t of za is just a constant. So an affine parameter is not unique, but it's unique up to a rescaling and a translation, and you can make this independently for every generator. Yeah, so do you understand what I'm talking about here? Affine parameter, and so where this surface is, so this surface is where the affine parameter x plus is supposed to be t of za. By changing the affine parameter, you can make this t just a constant. Yeah? So this will be the multiplicative change of the affine parameter. So this is convenient. And then you have you can derive this kind of a formula. Yes.
Changing the affine parameter doesn't change the surface gravity?
No, the surface gravity is defined invariantly by this formula, and the fact that k is the d by dt time shift at infinity. Yeah, but you still have a relevant point. It's the fact that k is really normalized relative to observers at infinity that makes the surface gravity unique. In the Rindler case, the analog of k is a boost, and a boost remains a boost everywhere. Yeah, so this becomes a translation. So the k here in Schwarzschild interpolates between a boost-like thing near the horizon and a translation-like thing near infinity, and that's possible because of the redshift effect. And in Minkowski, there's no such redshift effect. So this boost remains a boost, and you cannot normalize it. So in this sense, it depends then on the surface gravity is then a convention that comes in through how you measure the en route temperature with respect to what observer, how the observer is. So it is the observer is some accelerated person, yeah, on a rocket, and the acceleration of the rocket is, how strong is your engine, yeah. So it is, but it's not a property of the space-time, but of your engine. Whereas in Schwarzschild, really, it's the property of the space-time. So this is quite a difference between the two. Okay. Right. So now so you can do something, namely, you can look at the relative entropy So I'm going to call it S rel of T. So that's the relative entropy between your state and the Hartle-Hawking state. with respect to observers that dwell in this shifted wedge. So that's just a definition. But the point is that from monotonicity, the derivative of this, so as t is the surface, so if you shift that, if you slide that along scry, the shifted wedge becomes smaller, and therefore the relative entropy also becomes smaller. Yeah? So it's a special case of the monotonicity where if you like, the channel here in the data processing inequality is the inclusion channel. Yeah? So the inclusion of smaller algebra into bigger algebra is also a channel. Yeah? And if you apply the data processing inequality to this channel, you find that the derivative of this is always smaller. And I now claim that this gives the generalized second law, but I need to get myself a bit of space before that. But is the setup at least clear, or should I elaborate on it? Yeah, so the ingredients used so far are the Hartle-Hawking state and the fact that for a shifted wedge, I arguably know what the reduced density matrix is from the half-sided modular inclusion business, which I may also encode in this more well-defined formula. It's the same. These formulas contain the same information, and I'm using the monotonicity of the relative entropy.
Right.
Yeah.
So this formula with the modular monotonicity delta HHW, there's a Hartle-Hawking state restricted to that wedge.
Yeah, that's right. So the modular operator, you will know, of course, depends on the state, and that's the Hartle-Hawking state, but it also depends on the algebra. And here I'm using the algebra of the entire exterior, and here I'm using the algebra of the smaller. That's right. And accidentally, the ANEC in some sense can also be seen from this relationship here, because you can always show that the modular operator for a smaller region is larger. That's because its domain is smaller. I mean, that's the funny thing about modular theory. If you look at the Tometer operator, the definition is the same. It's always S of A of omega equals A star of the state. So once I presented 20 years ago, before this was fashionable, I gave a talk in, I don't remember, maybe Santa Barbara, and I explained, wrote the formula for the, for the modular operator, which, is like this. S of omega, E star of omega, and then I said it's also, you have to be careful. The domain of this operator is a set of vectors that you can write in this way. But the definition of the operator, if you forget about the domain, is always the same. It doesn't depend on which algebra you're referring this is from. And so people said this cannot make any sense, because it cannot be physically possible that some things depend on the domain. Yeah? So this is an extreme example where the formula is always the same for every algebra, but the domain is different and everything is in the domain. So this is expressed also here. Here the domain is smaller, and therefore the operator in this sense is bigger. And that gives a sign to this expression. Sorry for this, is just a digression. So let's see. I hope you've copied this out now. So let's see how we go from here to the do the generalized second law. So again, we have S real less than 0. And what's S real? So I'm going to write it with traces. So it's the reduced density matrix of the state. Let's call it Pt log of and so let me just define what is Pt is a density matrix of the state under consideration, and omega t is the reduced density matrix of the Hartle-Hawking state. And this is the formal formula for the relative entropy. And I also explained that this would be given by e to the minus 2 pi kt, and kt would be given by nu. Now, you can therefore take the logarithm formally of this. And this would be the terms from I plus, and you can take formally the logarithm of this. So a log of is minus 2 pi of kt. So you can rewrite this, the first term, and I already said that last lecture. The first looks basically like the von Neumann entropy, just with the minus. This is a minus the von Neumann entropy, and usually in this business it's just called the entanglement entropy of T, or of this state here. And minus this gives 2 pi times the expectation value of kt here in the state. And so you can formally write it like this. And at this, if you do it like this, you can. It's kind of easier to take the derivative. So let's now take the derivative. So here I'm just going to taking so d by dt of minus s. And so here the derivative I'm just going to write as a derivative and not do anything. And on the second term, I'm going to take a derivative. So the t appears down here in the integration domain, and it appears in the integrand, so I have to differentiate both. However, if I differentiate in the integration domain, so this means that the integral is from t to infinity. That means that the integrand is evaluated at the lower boundary, but due to this factor, it vanishes. So only contribution is when I differentiate t under the integral. And that gives me a minus integral of 2 pi, and then let's write out this is t theta mu nu, and then x plus yeah, how am I going to write it? Like this, so this like d as nu, like this, and d as nu I'm going to write as dx plus times dA times nu, volume element. So it can be written as t and then minus 2 pi integral from t to infinity dx plus, and then integral over the sphere dA theta k k, something like this. Okay, so now you see maybe where this is going. I'm now going to postulate the semi-classical Einstein equation. Which states that this was phi. Sorry about that. States that phi theta mu nu phi is going to be g mu nu, and the kk component will then give me here the Ricci tensor divided by appropriate powers of pi. So therefore, phi kk component pi is 1/4 g Newton times the Ricci tensor dotted twice into k. Yes. And the Ricci tensor can be expressed with my Ricciardori equation. So what was the Ricciardori equation? So my affine coordinate now is x plus. X plus is going up this way. It's an affine coordinate. So the Ricciardori equation is that this is the expansion in the plus direction. Derivative is minus expansion in this direction, and then a shear squared in this direction, and then minus Ricci plus plus. So k, little k. Okay. So you can think then that you can make a substitution here. First, replace the 2 pi times the expected stress tensor by 1/4 G Newton times the plus Ricci tensor. And then, after you made that, you replace the plus Ricci tensor, solving this equation in terms of the expansions and shears. So this would be all, looks very promising and nice. So you can, I'm doing this trivial algebraic step if you allow me to. So R++ is then minus shear, and then minus d plus expansion. So this is quite nice because you're going to afterwards integrate in x plus, so it's nice to have a derivative, so the integral is easy. These terms are not particularly easy to integrate, but they have a sign. I would so remember what we're trying here to calculate is this, and this was the relative entropy of T, and this had a sign. So if we minus R++, either you say it has a sign, or you say that's a kind of a dirty way to do it. You say this, after all, is a quantum correction, so there is an H bar here, or a G Newton, if you like, and this is a semi-classical approximation. So if G Newton is very large, nobody on Earth is going to trust that equation anyway. So G Newton is very small, so the expansion caused by this quantum stress energy tensor is going to be very small. The expansion of the generators in the background, Schwarzschild, is 0. So it's the expansion caused by the quantum effect is very small. So a square, and likewise the shear, the square is even smaller. And so you can either say it has a sign or you neglect it. So I would prefer to neglect it. Why? Because also nobody really believes that Einstein gravity is going to be the end of the story, but it's just an effective theory, and there will be all these other terms, higher curvature terms from higher effective theory corrections, or from alpha prime correction in string theory, whatever. So you're on the safer side to say that this is just negligible. And therefore you then just replace this 2 minus 2 pi by minus g minus r. So let's put a minus here. So minus r is plus, plus, plus. So you can replace this thing by 1/4 G Newton dx plus, and then dA d plus theta plus. And remember, maybe with my previous lecture, I was drawing this picture, and I'm going to draw it again, of some expanding geodesics. They start out in some parallel, and there's some area element dA, and then after a while there is a new area element dA later, and the expansion, of course, is telling you how different is this new area element from the old area element? That's intuitively what expanding means. And therefore, if you integrate that up, you learn that that this kind of expression, so you learn that this is minus S entanglement prime of T, and then you learn that this is minus, because the derivative is it's the lower side, yeah, so D is the upper minus lower, yeah, so you only keep the lower, so this would be the A prime. And as you see, this is has the form of the generalized second law, because everything was supposed to be less than 0, so therefore S entanglement entropy plus the area over 4 G Newton primed is greater than or equal to 0 if you cancel the minus signs. So this is the generalized second law, in the sense that the combination of the entanglement entropy plus 1/4 area changes as the change has a sign. Okay. Okay, that in a nutshell is the generalized second law. The assumptions here are the semi-classical Einstein equations, and the rest is a very nice interplay between algebraic quantum field theory, quantum information, and semi-classical physics. Now, I think I was going to say something about the QNAC, which is a kind of interesting variation on this, but I think the 15 minutes will not be really enough for that, and I'm just going to skip it. I think that's a nice way to end my lectures. In any way, you can read up on it in my lecture notes, of which what I've presented is a certain part, and some parts go beyond it. So, but you can read up on it, and in many other places too, of course. Thank you.
Many thanks to Stefan for the lecture. Now, any questions?
I think I just missed it, but why did you not get a contribution from the integrator?
I would have gotten one, but I'm saying that eventually this is going to settle down, and the expansion at late times is going to be negligible. So I just by hand say that there isn't a contribution from the upper bound. Now, that's not very suspicious, I would say. But that's a good question.
Any other questions?
You can still ask me personally, of course.
Where can one find your lecture notes?
They're on the archive.
Oh.
I gave the number. I can, if you want, I can write down the archive number again. Yeah, we can go for the break, and I'll write them on the board.
Okay, thanks again.